Hello world, welcome to LeetCode Legends. My name is Brian, and today I'm going to go over a really cool problem. Maximum profit in job scheduling, LC1235. Let's take a look at this bad boy. We have n jobs where every job is scheduled to be done from start time I to end time I, obtaining a profit of profit I. You're given the start time, end time, and profit arrays. Return the maximum profit you can take such that there are no two jobs in the subset with overlapping time range. So what this is sort of saying is we have a set of jobs and we can't do two jobs at the same time or more, only one at a time. Pick from the set of jobs the ones that will make you the most money. I think it's a pretty straightforward question. The reason it's rated hard is because they push you to have an optimal solution, and I'll take you through the different approaches we have here. All right, so here's an example scenario they gave. We have 4 jobs, and I'm showing them here in like a sorted order from bottom to top. How do we go about picking the optimal solution? Well, we're gonna have to consider like a predecessor job and a successor job. Can we choose the successor given the predecessor is already in, the golden set of scheduled jobs? So if we schedule the blue job and that's our predecessor, we can't schedule the yellow job. If we were considering the green job as the successor, then we can schedule it. What if we had by chance picked the yellow job as the predecessor? Then we can't schedule either the green or the black job because they conflict. There's an overlap. So the maximum profit for this scenario comes from scheduling the blue job and the black job. And we figured it out by trying out different predecessors and considering the other elements as successors. A great algorithm technique that does something like that is called backtracking. I think backtracking is always great to have in your back pocket when you're seeing like a dynamic programming question, because if you don't see the recurrence, then you can just basically sort of brute force it by using backtracking, and who knows, maybe your interviewer will be happy. So a quick note on job sorting. I'm gonna sort the jobs by end time. If you wanna do it by start time, you can. You have to tweak the approach a little bit towards the end. So another reason that we sort them is when you're looking at a sequence of jobs and you're looking at the golden set of scheduled jobs and you're considering a new job, considering adding that into this set, you only have to look at the 2 jobs, right? If the green job and the black job here conflict, you can't add it into the set. If they didn't conflict, then you can add it into the set and you don't have to check all of the preceding jobs because you've already done that check before, one at a time, and because of the sorted order. So, all right, let's take a look at the backtracking approach here. It's going to be time complexity O of 2 to the n, an exponential approach, because there's going to be 2 choices at every point in the recursion. Let's take a look. Okay, so here is the function that we have to implement. And as a first step here, I've taken the 3 arrays and merged them into a list of jobs. I don't want to work with 3 separate arrays. I want to just work with jobs, and each job has a end time, start time, and profit. And based on this ordering, I'm going to have everything sorted by end time with start time as a tiebreaker. And for backtracking, you always need a result variable that's passed in by reference, and each subproblem or each point in the recursion has a chance to update this variable. And I'm going to call this function solve. Solve will be my backtracking implementation. Let's go take a look at that. All right, so my solve function is going to be passed in jobs I. I is the index of the predecessor. J is the index of the current job we're considering adding into the scheduled list. And P is the running profit. Initially, we'll have 0 profit, and we're going to see if we can schedule some jobs and make some money. And lastly, the result array is passed in, and this is what's going to be updated when we reach the end of our search path. We're searching for solutions here in backtracking. So if the current job we're considering is actually like past the end of all the jobs, we've recursed all the way to the end, then at this point we can check if our running profit P is a new optimal solution, a new maximum. And we're going to make that check every single time we have considered all the jobs, and then return. Now, if we haven't passed all the jobs and we have some job J to consider, we're going to check if there is a predecessor and job J starts before the predecessor ends, then we have a conflict. We cannot schedule job J. We cannot make money on job J right now based on the predecessor that's already been chosen. So we just recurse and we increment J so that we consider the next job. The predecessor job stays the same. Else, we have 2 choices. We can either not take the profit for job J and just keep trying other jobs, or we can include the profit from job J and schedule it. And in that case, job J becomes the predecessor for the next phase in the recursion. So this is it. Feel free to pause the video if you want to take this in a bit more. Let's run it, make sure the local test cases pass, and submit. Let's see if we can make those LeetCode gods happy. They seem to be a little judgmental today. All right, so we got time limit exceeded and only 15 test cases passed. It's good we don't have a wrong answer, right? It's good that we have something going. But we're gonna have to make this algorithm faster to make the LeetCode gods happy. So let's recap that backtracking solution there. At every point in the recursion of the backtracking algorithm, we were given that job I was already scheduled and job I ended before job J. That's all we know. That we use those 2 things to find out if this new job conflicts with the golden set of scheduled jobs. And then at every point in the recursion, we had choices to make. Do we schedule the job J or do we not? All right, so when I was approaching this question, after I did the backtracking algorithm, I thought, hey, I have recursion here. Can I leverage this function and implement some dynamic programming approach? So the difference would be that instead of traversing all paths and only incrementing the results at the end, can we return a profit? Can we return the maximum profit from every point in the recursion and try to combine those subproblems into the ideal optimal dynamic programming solution? And the answer was yes, it worked. So The exact same properties are given at each point in the recursion, and we have the same choices. The only difference now is that when we make a choice, we want to find out what would be the max profit from making that choice. Like from that point onwards, what's the max amount of money we can make? And then we return the max of those two choices, scheduling or not scheduling. So what is the recurrence relations for this? So we're using two state variables, I and j, the preceding job and the current job, index I and j. Let dp of I and j equal the maximum profit scheduling job j through n, given job I is committed. If no overlap, dp of I and j equals max of dp of I and j plus 1, dp of j and j plus 1 plus profit j, else dp of I of j equals dp of I and j plus 1. Sorry, it's a mouthful, but basically we're just combining the scenarios that we were considering and just figuring out which one gives me a better maximum value. And we have to consider if there's overlap or not. If there's no overlap, we have the two choices to make. If there is overlap, then we only have one choice to make. And similarly to how the backtracking terminated, if we've considered all jobs and there's no more jobs that we can make money off of scheduling, right? So at that point, the recursion needs to return 0. There's no more profit. So let's take a look at the recursion tree here. Here we have a diagram drawn where we call this algorithm for n equals 5. There's 5 jobs that we can choose from. And there are 2 to the n subproblems here. And take note of how some of them are repeated. We're going to fix that by using memoization. So we take a look at that now with memoization, and we've reduced the number of problems from exponential number to a polynomial number of n squared. Let's take a look at this one in code. All right, so starting off here, again, we have our list of jobs that are sorted by n time. Going to define a dictionary that we're going to use for memoization, and we're going to return dp of jobs, I equals -1, j equals 0, and pass that memo table along so we can build up the solutions to our subproblems and solve the bigger problems in the end. So here's the implementation of the dynamic programming top-down solution. So first, I form a key for using in the memo table. This is just forming a key from I and j so we can cache the solutions to our subproblems. If we haven't computed the solution for this subproblem before, let's put our base case into this memoization table. So if there are no more jobs left, then the profit for that would be 0. So for this I and j, it would be 0. Else, if we still have jobs to consider and there is a conflict, we only have one choice to make. So the max profit we will make is just whatever the next job can make. If there is no overlap, then we have to return the max of these 2 paths. One path is choosing not to schedule job j, and one path is scheduling job J. So if you schedule job J, we're going to take the money from it, right? You want your money, you want to be paid when you do work, and you consider how much more profit can you make scheduling the next job when job J is now the predecessor. Let's give this a whirl, shall we? See if this pleases the LeetCode gods. Before we had 15 test cases pass, let's see where we end up. So 22 test cases passed now, but we hit a new problem also. Our memory limit was exceeded. So that means our algorithm is using more space than the LeetCode gods want us to. This isn't like a new problem like compared to the previous solution. It's just a problem that's showing up now because we're getting through more tests. Both of those solutions, backtracking and this one, use O of n squared space. Sorry, the backtracking would have been O 2 to the n, but ignore me for now. All right, let's see. We just need to make this better. So can we do better? Yeah, we can, right? So the current space complexity, like I said, is O of n squared because we have two state variables in our dynamic programming approach. Something to take note of was that in our recurrence relation that we had, you see that the current subproblem solution only depends on one column in this 2D array, this J plus one column. It's looking at different elements in that row, but it's looking at the same column. So we don't need a full table at any one point in time. We only need a row. So that's going to be proof that we can improve space. So let's try to approach the question a little differently. So do we need two state variables? No, because we know we can get rid of the full table. So let dp of j be the maximum profit scheduling jobs 0 through j. So now we've taken I out of the dp definition. And to compute dpj though, we're going to do iteration. We're going to iterate over all predecessors from 0 to j minus 1. Let me show you what I'm talking about. So if job j happens to be the black job, we're going to iterate and consider all of the previous jobs as potential predecessors. So if there's no job at all, we can default and say that the profit is going to be 70. So if the blue job is job I, we take a look at that as a potential predecessor. We see that it doesn't overlap and it can be combined with 70, the black job. And so the profit for this scenario would be 120. If job I is the predecessor, then you can't actually even consider it. It conflicts. So the max profit for the scenario is 10, but we actually wouldn't even consider it when we code this up because it's not going to be better, right? And when the green job is job I, we see that it can't be combined with job J. It can be combined with the blue job, but that's not what we're going for here, right? We're comparing every job to the black job. So this is what I meant by we're going to iterate for all I less than j. So for those scenarios, the best solution is when I had been 0, j and j is 3, at that point we had our optimal solution. So dp of j is 120. So here's the recurrence relation restated one more time with a little bit more clarity. One point that I didn't touch on so far is that we want dp of j to include the possibility that the jth job doesn't help you. Like what if the black job actually started before all the prior jobs and made it so you couldn't include any of them? Then you might want to consider the possibility that it doesn't help you, and consider the possibility that the previous job j-1 was the best. So here we have dp of j equals max of dp j-1, dp of j, and dp of I plus the contribution of job j. And we consider all three of those scenarios for all I less than j. Let's take a look at this solution in code. It will be more clear, I think, than just looking at the recurrence relation. Okay, so the only difference here is I'm going to use a list for the memo table because now my keys are simpler now. I don't have my key as being a pair of I and j. It's just a key of a single integer. And I'm not going to use like the -1 trick that I was using earlier. Just we're iterating from 0 to j-1 every time. So the memo table is defined and passed into the dp function. The dp function only takes one state variable now, just j. I is going to be done in iteration within the recursion. So we have some memoization here to avoid repeating the calculation of subproblems. All right, so initially the result of dp of j will be set to the profit of job j. So that considers what if job j would give us $1 million. I don't want to consider any other job. I'm just going to do job j. Leave me alone. Don't even want to solve this problem. I'm going to go do that job. All right, so for I in range 0 to j-1, we're going to do the iteration that I detailed in the overview and check if job j and job I can be combined. So there's no conflict if this check succeeds. If there's no conflict, then let's see if we can update our result so far, and by comparing it and seeing if this can give us a new max where we take the profit from job j and add it to the best that we can do considering the first I jobs. And we do that for all the potential predecessors of job j. And then after we finish that, we have one more check. If there is the possibility of not including job j, and if that is a greater profit than including job j, let's use that value. So that's the scenario I'm talking about, where say the black job started before all the other jobs in the list and its profit was only 10. I wouldn't really want to do that. Like, having considered all the j jobs, I still wouldn't want to include job j in my solution. I want one of the predecessors only, right? Not job j. So let's run this and submit. Come on, LeetCode gods, just be happy. Time limit exceeded. Okay, so we got rid of that memory error. We did optimize space, but we're still stuck at the same place. Now we're just too slow. All right. So can we do better? So what if we search backwards from the job J minus 1, 0, right? So we're looking at the black job as job J, and we just search backwards looking for the first job that doesn't overlap. Given how we've defined our DP function, where like DP of J equals the max amount of money you can make considering J jobs, then that's the only one we need to look at. We just find the first J or I, whichever variable you want to use, find the first I where that job I doesn't overlap with job J, and then add those up, and that's the best you can do if you're combining jobs, right? So what we just talked about was like a linear search from J back to 0 in the worst case. So that's still not really helping us. It's going to still be, we're still iterating over all I from 0 to J minus 1, but just going backwards. It would likely be better on the average case because we would likely find that one job quicker going from the right. But what about binary search, right? We've talked about how this list of jobs is sorted, and it's sorted by end time. What if we were to binary search for a job that ends just before our current job starts? Sounds like a great idea. All right, let's take a look at this code. Okay, so here we are. We have the same list of jobs sorted by end time, and I'm going to pass control over to my function solve here. So here I actually converted from top-down dynamic programming to bottom-up just to make this a little bit more clear. So here we have a DP array initialized to the profit of each one of the jobs. And we iterate from J will sweep from 1 to N, and we're going to build these subproblems up left to right. So we're going to search for a job that ends just before job J starts. If such a job exists, then we're going to see if combining it with job J will give you a new best score, right? A new maximum. And then, as always, we don't want to assume that this job J will be included in the golden set. So we consider the possibility that not considering it at all might be better than considering it to be included. So we're going to iterate over all possible jobs from 1 to N and search for the predecessor. And by the end of this loop, we will be returning the optimal solution. Up above here is the binary search implementation that I came up with. And the only difference between this and normal binary search is that I'm not ever happy with a given target because we can have duplicates in this array. So like there can be multiple jobs that ended at 4, and I have to make sure that I consider the one that precedes, job J in the sorted order. So basically, whenever you're considering a job, you have to check, is it less than or equal to the start time T of my current job? If it is, we consider it as a possible result and then keep narrowing in our binary search window and then see if we can get an even better solution, like a job that ends even closer to our start time. And this is pretty much it. Let's try to run this. We've made the LeetCode gods happy. I'm incredibly happy. I hope you enjoyed the journey to pleasing them. One thing to notice here is that this solution only beats 5% of other Python users. Thought that was sort of funny. When I looked at their other submissions, what I saw was there's a different approach in Python where you can use a priority queue. And for whatever reason, that performs a lot better in Python than the dynamic programming approach. But per my understanding, they're both the same time complexity. I think it's just more iteration in Python that we're doing in the dynamic programming algorithm slows it down a bit. Okay, so to wrap this tutorial up, what were the key points from this tutorial, right? There's a lot of code here. I'll share it in the description. The key points here are listed out here. I can go through them. So as I mentioned earlier on, keep backtracking in your back pocket. If you can't come up with a solution, the elegant DP solution, try backtracking and maybe your interviewer will be happy with your approach. It's better to have something that works than doesn't. Also in the real world, maybe the backtracking approach is all you need and it would be typically a lot simpler to understand. A common thing to look for is like when you implement a dynamic programming solution, if you see that your recurrence relation isn't using the full table at any point in time, you usually can optimize it and you can reduce the amount of space you're using. For instance, like a Fibonacci algorithm, right? You can do a solution that uses linear space, and then you can realize that, oh, I'm only looking at 2 variables that are 2 elements at a time for my row. What if I just had 2 variables instead of a whole array? So that's a very simple case. But in this one, we optimize from having a 2D table to having a 1D array. A common approach to solving dynamic programming questions is something that we did here is we just reframed the original question. What is the maximum profit from scheduling jobs? And we reframed it and said, what's the maximum profit scheduling J jobs? And that turned out to be the optimal solution, just with a little bit of binary search magic. Sorting always helps with interval problems. That's something that we should all have ingrained in us. The more interval problems you do, you'll see like you always sort. And even great DP algorithms can sometimes be made better, right? We don't have to just say, oh, I use DP, I eliminated computing redundant subproblems, you can look for other optimizations. This optimization with using binary search is only possible because of sorting, the fact that they're sorted, and sort of the way that we were iterating too, it also required that you're sorted by end time. If we were iterating from the other side, I think we can use start time. One last point is definitely study common patterns in DP questions. So the pattern we used here was iteration and the recursion. This comes up a lot in questions with sequences and subsequences. The fundamental problem to make sure you know is longest increasing subsequence. So that's the question that sort of introduces iteration and the recursion. You can do it without iteration and recursion, similar to what I did here, but you're going to use a lot more space. And that's all I have for you guys. Thank you for joining me for this tutorial. This is a hard question. When I solved this question, it took me all day, so don't feel bad if this is one you struggle on. It's a great one for really, cementing in your DP knowledge and trying to also push to the next level. How can I make my initial dynamic programming algorithm better? So thanks again for joining us. Signing off.